Welcome to Chapter 11, Introduction to Three-Dimensional Geometry. While we've studied points in a plane using two coordinates, real life often requires three dimensions. Think of a ball thrown in space, an aeroplane flying, or a ceiling fan. All need three coordinates to locate. The great mathematician Leonhard Euler helped develop these concepts. We'll extend our 2D knowledge to 3D space. In three dimensions, we have three coordinate axes. Imagine three planes intersecting at point O, all mutually perpendicular. The lines where they intersect are called the x-axis, x prime OX, y-axis, y prime OY, and z-axis, z prime OZ. These three axes form what we call the rectangular coordinate system in three dimensions. They're all perpendicular to each other. The three coordinate planes are the xy plane, horizontal, called XOY, the yz plane, called YOZ, and the zx plane, called ZOX. Think of the xy plane as the floor, and the other two as perpendicular walls. These three planes are mutually perpendicular to each other, just like the floor and two adjacent walls of a room. Just as two perpendicular lines divide a plane into four quadrants, three perpendicular planes divide space into 8 parts called octants. They're named XOYZ, X prime OYZ, X prime OY prime Z, and so on. We denote them by Roman numerals I through VAID. Each octant has a different combination of positive and negative coordinates. The sign convention follows naturally. Distances measured along OX, OY, and OZ are positive. Distances measured along OX prime, OY prime, and OZ prime are negative. For example, in octant I, all coordinates are positive, plus, plus, plus. In octant 8, the signs are plus, minus, minus. The signs tell you which octant a point lies in. A point P in space has three coordinates, x, y, z. The x-coordinate is the perpendicular distance from the yz plane. The y-coordinate is the perpendicular distance from the zx plane. The z-coordinate is the perpendicular distance from the xy plane. Together, these three numbers uniquely determine the point's position in space. To find the coordinates of a point P, we use a step-by-step process. First, drop a perpendicular PM to the xy plane. Then, from point M, draw a perpendicular ML to the x-axis, meeting it at L. The distances are OL equals x, LM equals y, and MP equals z. So the coordinates of P are x, y, z. Special points have simple coordinates. The origin O is at 0, 0, 0. Any point on the x-axis has coordinates x, 0, 0. Only x is non-zero. Similarly, points on the y-axis are 0, y, 0, and points on the z-axis are 0, 0, z. Two coordinates are always 0 for points on axes. Points on coordinate planes have one coordinate 0. A point in the xy plane has coordinates x, y, 0. The z-coordinate is 0 because it's on the xy plane. Similarly, points in the yz plane are 0, yz, and points in the zx plane are x, 0, z. One coordinate is always 0 for points on coordinate planes. Here's the complete sign pattern for all 8 octants. Octant 1 plus plus plus, octant 2 minus plus plus, octant 3 minus minus plus, octant 4 plus minus plus, octant 5 plus plus minus, octant 6 minus plus minus, octant 7 minus minus minus, octant 8 plus minus minus. Memorize this pattern. The distance between 2 points P with coordinates x1, y1, z1 and Q with coordinates x2, y2, z2 is given by PQ equals the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. This is the 3D extension of the 2D distance formula based on the 3D Pythagorean theorem. The distance from the origin to any point Q with coordinates x, y, z is the square root of x squared plus y squared plus z squared. This is a special case of the distance formula where one point is the origin. For example, the distance of point 3, 4, 5 from the origin is the square root of 9 plus 16 plus 25, which equals the square root of 50. 3 points P, Q, and R are collinear if they lie on the same straight line. We check this by verifying that PQ plus QR equals PR. This is the same condition we used in 2D geometry. Calculate all three distances using the distance formula, and if the sum of 2 equals the third, the points are collinear. The section formula in 3D finds a point dividing a line segment in a given ratio. If point R divides PQ in ratio n, then R's coordinates are mx2 plus nx1 over m plus n, my2 plus ny1 over m plus n, mz2 plus nz1 over m plus n. This extends naturally from the 2D section formula by adding the z-coordinate. The midpoint formula is a special case of the section formula when m equals n. The midpoint m of segment joining p of x1, y1, z1 and q of x2, y2, z2 is x1 plus x2 over 2, y1 plus y2 over 2, z1 plus z2 over 2. Simply take the average of corresponding coordinates. This divides the segment in ratio 1:1. Three-dimensional geometry has many real-life applications. GPS navigation systems use 3D coordinates to locate positions on Earth. Computer graphics and 3D modeling rely heavily on these concepts. Architects and engineers use 3D geometry in construction. In physics, we describe motion through space using 3 coordinates. To verify if 3 points form a right triangle, use the distance formula to find all 3 sides. Then check if the Pythagorean theorem holds. The sum of squares of 2 sides should equal the square of the third side. If this is true for any pair of sides, the triangle is right-angled at the third vertex. To verify if 4 points form a parallelogram, check that opposite sides are equal in length. Use the distance formula to calculate all 4 sides. If AB equals CD and BC equals DA, then ABCD is a parallelogram. Note that the diagonals may not be equal. If they are, it's also a rectangle. Watch out for common mistakes. Don't mix up the order of coordinates. It's always x, y, z. Be careful with signs when determining octants. Remember that points on coordinate planes have one coordinate 0, not 2. When applying the distance formula, make sure you're subtracting corresponding coordinates correctly. Key formulas to memorize. Distance between 2 points, square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Distance from origin, square root of x squared plus y squared plus z squared. Section formula, weighted average of coordinates. Midpoint, average of corresponding coordinates. Problem-solving strategy. First, identify the coordinates of all points involved. Apply the appropriate formula based on what you need to find, distance, midpoint, or section point. For geometric verifications, check the relevant conditions, collinearity, right angle, or equal sides. When possible, visualize the situation in 3D space. Let's find the distance between P of 1, -3, 4, and Q, -4, 1, 2. Using the formula, PQ equals the square root of -4 minus 1 squared, plus 1 minus -3 squared, plus 2 minus 4 squared. That's the square root of -5 squared plus 4 squared plus -2 squared, which equals the square root of 25 plus 16 plus 4, giving the square root of 45, or 3 times the square root of 5. Check if points P of -2, 3, 5, Q, 1, 2, 3, and R, 7, 0, -1 are collinear. Calculate. PQ equals the square root of 14. QR equals 2 times the square root of 14. PR equals 3 times the square root of 14. Since PQ plus QR equals the square root of 14 plus 2 times the square root of 14 equals 3 times the square root of 14, which equals PR, the points are collinear. Find the octant for point -3, 1, 2. The x-coordinate is negative, y is positive, and z is positive. Looking at the sign table, negative plus plus corresponds to octant 2. For point -3, 1, -2, the signs are negative plus negative, which corresponds to octant cis. The signs determine the octant. In this chapter, we learned that the 3D coordinate system has 3 axes and 3 planes. A point is located by 3 coordinates, x, y, z. The 8 octants are determined by the signs of the coordinates. The distance formula extends naturally from 2D to 3D by adding the z component. The section and midpoint formulas also extend by including the z coordinate. Thank you for joining Chapter 11 on Introduction to Three-Dimensional Geometry.